Okay, so in this next screencast video for Math 1410, we're going to introduce the cross product. So this is from section 3.4 in the textbook. This will be the first of two videos going over material on the cross product. So we'll see next week that the cross product is going to be necessary for coming up with equations of planes in a lot of situations. Okay. So, what is the cross product? So the cross product is a way of combining two vectors to get a vector, right? So remember that the dot product, so we already defined the dot product, so the dot product gives me a number, right? So just as a reminder, let's put this down here at the bottom. The dot product, u dot v, the outcome there is a number. It's simply u1 times v1 plus u2 times v2 plus u3 times v3, right? This is a number. Okay. The cross product, on the other hand, the cross product is a vector. So it's important to keep track of the fact that one of these guys is a number, one of them is a vector, and again notice that there is no product where we take the kind of, so in the dot product we're multiplying the corresponding components, but we don't take those as components of a new vector. We add them up to get a number, and there, there is no situation where we actually want to take those as components of a new vector. It could give us a new vector, but that vector is not interesting. So the way to get out a new vector from two vectors in 3 dimensions that is useful is using the cross product. And this formula here, this formula is fairly intimidating the first time you see it. And so what we're going to do is we're going to go over basically some methods for computing this thing, for remembering this formula, because it's a complicated looking formula. But it's a complicated looking formula because it does sort of a complicated job. It has sort of a sophisticated setup, right? And so the reason that you do the cross product, the job of the cross product is right here. This point here is key. Okay. This is what you need to know as far as how do you determine the direction of the cross product. The vectors u and v that you put in, right? They're going to be, say here's u, okay, and here is v. All right. Now, any two vectors like that, as long as they're not parallel. So for parallel vectors, you just say the cross product is 0, and we can work out that the cross product of parallel vectors is 0 using this algebraic definition. It's not too hard to see that. But for non-parallel vectors, any two non-parallel vectors, they span a plane, right? So there's a plane here containing those two vectors. And you want the direction of the cross product to be perpendicular to that plane. So you want the cross product orthogonal to both of the vectors you put in. So the cross product, looks something like this. U cross V. And we'll see, I mean, you could take this if you want as a geometric definition, but we'll be able to prove that this is true, that if you construct the parallelogram spanned by those two vectors and you want to calculate the area of that parallelogram, the area of that parallelogram is equal to the magnitude of the cross product, right? So the direction is more or less determined by this requirement that it be perpendicular to the plane containing the two vectors that you put in. The way you just assign the magnitude is by this kind of area rule. And the fact that the cross product computes an area makes it useful for a lot of applications. But this orthogonality is also very important because when we get to the discussion of finding equations for planes, we're going to see that one of the things that we need what's called a normal vector. We need something which is perpendicular to the plane. And this gives me a method of constructing that normal vector. Now, remember, what does orthogonality mean in this context? The fact that it's orthogonal to both u and v. Remember that orthogonality is encoded using the dot product. So what we're saying here is that the dot product of u with the cross product is equal to 0. And the same thing is true if we take the dot product with v. Okay. So how do you actually remember this formula? It's a scary looking formula. How does this work? Well, let's see how things would work in an example. Let's say I take u is equal to minus 1 4 3. I'll take v equal to 2 minus 3. Let's go with 7. Okay. So the cross product, u cross v. So here's our formula, right? We have this formula for u2 v3 minus u3 v2 in the first entry. Then u3 v1 minus u1 v3 in the second spot. Then u1 v2 minus u2 v1 in the third spot. And so, I mean, you can kind of notice there is a pattern, that you have 2, 3, so the index on the u kind of goes up by 1, so it's 2 followed by 3, then 3 followed by 1. I mean, if you kind of think of them as being in a circle, you have 1 is followed by 2, 2 is followed by 3, and then 3 comes back to 1. And so if you sort of cycle the indices around, 2, 3, 2, 3, so we kind of do this, right? So the first one is 2, 3, and then the next one we kind of go one step along, we go 3, 1, and then the next one along we go 1, 2. So you kind of keep doing steps along the circle. So you can try to remember it that way if you want. We'll see some other methods right away, but that's one way. Some people are actually quite happy just kind of remembering this pattern and going with it. But the only problem with remembering the pattern is then you've got to do some pattern matching, right? So you've got to now kind of identify things. So u2, now we kind of go up here. So here's u1, here's u2, here's u3, right? And you start plugging things in. So u2 is 4, v3 7, u3 is 3, v2 is minus 3. All right, then u3, 3 times v1, which is 2, minus u1, minus 1, v3 is 7, and then u1 minus 1 times v2, which is minus 3, we're running short on space here, subtract u2, 4 times v1, which is 2. Okay, so let's work this out. So 4 times 7, 28, plus 9 gives me 37. 6 plus 7 gives me 13. And then this is 3 minus 8. Negative 5 gives me the cross product. One thing you might notice is if I were to do, let's say, u dot, u dotted with u cross v. Here's one way we can check to see, did we do things correctly? If I do minus 1, 4, 3 dot product with 37, 13, minus 5. The previous slide said this should come out to be 0. Let's see. Minus 37, minus 1 times 37 gives me minus 37, plus 4 times 13, minus 3 times 5. So 4 times 13 is, that's going to come out to be 52, 26 plus 26. This, of course, is 15. So minus 37 minus 15 comes out to minus 52 added to 52. This does indeed give us 0 as we expected. You could check for the vector v if you want, but we'll just do the 1. Okay, so what are some other ways you can try to remember this cross product? So one way to remember, and this kind of gets us set up for things we'll do later anyway, is to remember the cross product in terms of what are called determinants. So a 2 by 2 determinant is basically a way to take a array of numbers, a 2 by 2 array, and by 2, so 2 rows and two columns. That's what we mean by 2 by 2, right? It's 2 across, it's 2 down, 2 rows, 2 columns, and you do this diagonal here, so you do A times D, and that one comes with a plus sign, and then you do B times C, and that one comes with a minus sign. So you do one diagonal minus the other diagonal. So A times D minus B times C, and that gives you the determinant. And so you can remember it this way. So the cross product is given, and remember our ijk, these are our unit vectors, so we could also think of this as, if we want to write it in angle form, u2, u3, v2, v3, u3, u1, v3, v1, u1, v1, u2, v2. You can remember it that way. There's still the matter of trying to remember which indices go where, 2, 3, 3, 1, 1, 2. So there's still some work to kind of keep track of things there. But some people find it kind of easier to remember these guys, and as far as putting things in the right places. So if we went back to our previous example, so what was our previous example? Minus 1, 4, 3. V was 2 minus 3, 7, and you can work out that the cross product is going to be, so we do 4, 3, minus 3, 7 times I, and then we do 3, 7, minus 1, 2 times J, and then we do minus 1, 4, 2, minus 3 times K. Right? And then you work out those 2 by 2 determinants, and you find that they come out to be the same as before. 28 plus 9, so 37I, 6 plus 7, right? Because notice you're doing minus minus. Remember, you've got this minus sign up here, right? So 3 times 2 is 6. 7 times minus 1 is minus 7, so 6 minus minus 7 gives you your 13J, and then minus 1 times minus 3 is plus 3. 3 subtract 4 times 2, so 3 minus 8 gives you minus 5K, the same as before. So you can remember it that way. And one way you can sort of think of this is, when you're doing the I component, right, you cover up the I component, so you cover up the I component here, and then you write down the 4 numbers that are left over, okay? 4, 3, minus 3, 7. And then and that works for the K component as well. If I cover up the last 2 entries, I'm left with the minus 1, 4, 2, minus 3, and I put those ones down. The only one that's kind of a little bit of an oddball is the one in the middle, because when you cover up J, well, then you've got the numbers on the outside, the minus 1, the 3, the 2, and the 7. And notice that the 3 and the 7 come before the minus 1 and the 2. So you kind of always, I guess the way to think about it is you cover up an entry, so you cover up one of the components, and then you work your way to the right, and then you cycle around once you reach the end. Okay. So the other way you can remember this is using a certain 3 by 3 array, and we'll see later on that this expansion rule for this 3 by 3 array, it does correspond to the expansion rule for a 3 by 3 determinant when we define determinants later on. But for now, we'll just kind of use this as a way of remembering the cross product. Notice, and this is again quite important, there are minus signs showing up in these 2 by 2 determinants, but there's also a minus sign here. Okay, so beware that minus sign. And let me just kind of underline things here so we don't cover stuff up. That minus sign is important. If you don't like the minus sign, one of the things that you might notice is that if you take your determinant and you swap the 2 rows, or the 2 columns rather, then this would become, we again do this sort of, we do this product minus that product, so this one plus this one minus. Then we have C times B, so we would have I guess we wrote it the other way around, but let's do it this way. So this would be BC minus AD, and if I pull a negative out, that's minus AD minus BC, and that in turn is the negative of what we would get if we did A, B, C, D, right? So if you swap the columns, that amounts to a minus sign. So the other way you could write this here is you could write this as plus U3 V3 U1 V1 times J, and then that's exactly the same as the formula that we had on the previous slide. Okay, I think we left room for an example, so let's put that on the next slide. So let's say I want to do U cross, let's actually write down what these guys are. So let's say U equals 2 minus 1, 0. V is equal to 1, 3 minus 1. Then I can calculate the cross product by building this 3 by 3 array, I, J, K. So I write down U first, then I write down V, like so. And the way you do this expansion, so the way you think about this expansion rule here is when you want the I component, you go over here, here's the I component, you strike out the row and the column that contain that entry, and you write down the 4 numbers that are left over, and that's what you see here, right? And then when you get to the J, you do the same thing. You strike out the row and column containing the J, and you write down what's left over. So going back to here, we say, okay, oops, if I kind of delete the row and the column containing the I, then what I'm left with is minus 1, 0, 3, minus 1 times I. And if I delete, let's do another color here. If I delete the row and the column containing J, and I write down what's left over, and if I'm careful to remember that there's this minus sign in the middle, 2, 0, 1, minus 1 times J. And then if I do the K, so I do this row and the last column, and I write down the numbers that are left over, I've got 2 minus 1, 1, 3 times K. And so be careful, make sure you remember this. The main mistake people are going to make again is this minus sign. So the one in the middle comes with a minus sign. Otherwise, we just have to do these 2 by 2 determinants. So this one we do 1 times 1, that's 1 minus 0, so we just get 1 times I minus, let's put that minus sign down now before we forget. 2 times minus 1 gives me minus 2, and then 1 times 0 is 0, right? So it's minus 2 subtract nothing, leaves me with minus 2. J, and then 2 times 3 is 6, right? So going across, so this gives me plus 6. And going this way, I get minus 1. So that's plus 1. So 6 plus 1 gives me 7k, leaving me with the vector 1, 2, 7 for the cross product. Okay, and every other cross product is going to be the exact same story. The only thing we can really change on you are the numbers. Otherwise, the procedure is exactly the same. One of the things, let's just confirm one thing before we go on. I told you at the beginning that if one of your vectors is a multiple of the other, then the cross product should be 0, right? The cross product should give 0 for parallel vectors. And also, if you change the order, you get a minus sign. We'll go over some of those in the next video. But as far as the parallel vector rule, let's say I take W to be let's take any a times u, where a is a sum number, right? So 2a minus a 0. And if you think about what happens when you do u cross w, so I, j, k, and I'd have 2 minus 1, 0, 2a minus a 0, and you expand. So, well, the first one, we get that, minus j times 2a 0, 0, k times 2 minus 1, 2a minus a. Now, the fact that I've got zeros makes things easy. It's pretty, it's obvious that that's going to be 0. That's going to be 0 because you're multiplying, both of the entries on the left get multiplied by 0 when you calculate those 2 by 2 determinants. But even this one, notice that 2 times minus a, so you get 2 times minus a, and then subtract minus 1 times 2a, right? You can take that a and you can factor it out, and then what are you left with? You're left with 2 times minus 1 subtract minus 1 times 2. Well, that's always going to give you 0, right? This is a times 0, so you get 0. So that one is 0 as well, and so you get the 0 vector, and this is something that happens in general. Okay, so we'll look more at properties when we get to the next video.